This year, Professor Andrew Davison gave a presentation at ICRA in a workshop titled Spatial AI. I thought it was interesting. There's two things I want to talk about here. One is the question of representation, and the other is the question of hardware. Both are crucial for robotics because I think we are entering now a time when the idea of robotics or the concept of robotics is actually hitting the real world, and that's happening through self-driving cars. And we said that many times, that we believe that the self-driving car is sort of the killer app for real world AI. We thought it's going to be the killer app for AI, but GPT came ahead of us for that. So we actually solved language before we solved spatial AI, which was not expected 5-6 years ago. Nevertheless, for real world AI, for physics and the real world and the interaction and spatial AI and all those sort of things, it's the self-driving car that has penetrated the real world. We have millions of customers driving with Tesla's FSD. We also have people using Waymo, although that is more like a car on digital rails. But the Tesla FSD is real world AI in a sense that it's intelligent, it reacts to its environment, it has spatial intelligence, and it has been trained on a data set that actually reflects the problem which it's supposed to solve, and that is driving around in the real world. And fundamentally, most fundamentally, it has spatial intelligence because it is possible to make decisions such as moving in space, deciding, things like what is in front of me, what is behind me, deciding what angle something is coming at me, all those sort of things. The self-driving car has that ability. Now, the pushback from the academic community is already, well, self-driving cars are easy because it's a predefined structure environment, etc. I think they're just moving the target because a lot of the academics feel kind of left behind here, and also because it's Tesla. There's also some anti-Musk sentiment in the academic community and all that kind of stuff. But I don't want to talk about that right now. That warrants its own podcast. I think what we want to talk about here is really fundamentally talk about Andrew Davison's two main topics in his presentation. He's one of our go-to professors that we listen to. I think he's relevant. So the question of representation and then the question of hardware. This is not even a podcast. It's June 26, 2026. This is Krim Delco. For the year, we're down 10%. The market's up 7, we're underperforming by 17%. So Davison gave a presentation at ICRA 2026, that conference we did not attend this year, and it was about spatial AI. And the idea here is to think about how we can introduce spatial intelligence into embodied devices. So this is intelligence that moves around in a physical body, that moves around in a physical space, and the question, like I said in the prelude, there's two fundamental questions here. One is the kinds of representations that we might need or that are useful to achieve that kind of intelligence, and then also the question of hardware. Let's talk about the representation. So the representation came also, this is a topic that we spoke about with Ranjay Krishna already, the professor at Paul Allen School of Computer Science. The idea is that, look, we start with pixels and we get to torque. And the question is, can we train our AI in a way that we have some representation in between that accelerates the learning and inference? So is it really efficient to go from pixel to torque? Can we find, can we find better representation? And of course, this is a fundamentally relevant question. For example, the choice of training data in itself is a representation, right? We're making a choice here. We're deciding that, for example, when Tesla full self-driving was trained, it was trained on videos of actual people driving the car. So somebody made the decision that in order to learn this task, the best would be to represent the problem in, of course, in this case, in the native way. And it is exactly what the driver is seeing. And since we want to mimic the driver, let's just use the same data, and the cameras of the car are approximating what the driver is seeing. In fact, they're making it even better and easier for the car to see things, and combine that with actuator data and then train that. So that was, so the way we the training data itself that we choose is already a choice of representation. I think we at Orange Capital Partners, we have our own credo, which is the robot learning pipeline, and it starts with training, with learning from video representations. So that is our view. Now, the academics are not in that field, or at least most of them are not. Some are. I think what people like Andrew Davison are trying to do is try to find better ways to represent. So don't just take a video and learn from it. Maybe you can also build priors, learn priors from data, but build priors. For example, a shape is something else than a fluid, or a fluid has a certain shape, or like, are there certain things that we can set the priors to that enable the the learning, the learning. And again, we at Orange Capital Partners are sort of in the camp of no, actually, that's not the most important representation. Is, again, it's the choice of learning. So what are we? How are we learning, and what are we learning from? What kind of data? And then let scale do its work. So have a pre-trained model that learns about spatial relationships. And the best way to do this is, again, internet scale video data. So that would be our take. It's not Davison's take, although he does say, to be fair to him, that he's agnostic to what kind of representations are necessary. He just thinks there should be some representation. And again, we contrast that with, like, yes, of course there should be some. We're not just going to randomly train from everything and then somehow hope to get spatial intelligence. We're going to focus on video from actual people doing things in the real world. The reason we use videos is just that we have the scale. And then we use the mid-training phase, which we spoke about Aviral Kumar's approach of reinforcement learning with correction. We spoke about, Shuren Song's approach with having imitation learning through special devices. The mid-training phase is the phase where we train the robot to actually learn skills. And then the third phase is the robot in the loop, where we want the robot now to go out there, and we have a model that allows for counterfactuals. Again, here, the representation is the actual counterfactual. Like, we have to give the robot the choice to choose between different options to execute tasks. And some of them could be the robot actually executing the tasks and learning from experience. And then there could also be some, let's say, shadow mode, a model that runs in the background and makes decisions in shadow mode. We could have simulation in the loop, a presentation we recently saw from the University of San Diego, University of California, San Diego, where we simulate while we're executing on policy, and then use trajectories from the simulator to execute and then feedback. But the point is, we want to have the robot in the loop. We want to use the robot as a data collection engine. So this brings us to the next point that Davison talks about, something that also is very dear to our heart here at Orange Capital Partners as investors, and that is the actual hardware, the technology required to build billions and billions of devices, whether it's humanoid robots and or other types of physical AI that is able to function in the real world, in real time, move around, and use real intelligence, which is, the ability to solve problems in real time at scale by being exposed to the environment. And he's talking about the hardware that's required. He's talking about a graph network of smaller devices, and the problem here being memory data going back and forth. So you have a more asynchronous, decentralized compute and memory, and then communicate through a graph network. What you're doing here, of course, is replacing the I/O with network overhead, and there's networking costs and things like that. Now this could be maybe solved with some sort of wireless technology, optical technology, those sort of things. So there are options on both sides. I think for us here, what's important, as investors in Tesla, of course, and NVIDIA, we're incredibly interested in the hardware side of things. Elon Musk has spoken about the necessity to redesign the chip industry for robotics. And I guess that's part of what he's talking about here, that, we need a rethink of how silicon is developed for a fleet of intelligent systems moving around in the real world and executing tasks that are autonomous, that are also in network. For example, the robotaxi network will be a network coordinating as a network, solving point-to-point solutions, but also solving network problems. So these are new types of compute problems. They require a rethink of the stack, and Musk is starting, of course, with the chips, but this is a lot, it goes all the way up to the stack, from the silicon all the way through all the layers to the application layer. And I think that's sort of where we see this going. Davison talks about the necessity. He mentions GraphCore, a company in the UK. There's several solutions here, because when we're talking robotics, of course, we're talking a much broader sense of solutions. One is a humanoid robot, but there's many other types of robotics opportunities and also problems and solutions to be pursued. So to summarize, Andrew Davison's presentation at ICRA 2026 focuses on two interesting questions of robotics. One is representation for learning and inference, and the other is the hardware necessary for a large global fleet of intelligence embodied systems. Both of these need a rethink, and here at Launch Capital Partners, we're involved in both of these interesting topics. Thank you.